Greetings to one and all. My name is Dr. Subhranshu Padhi, and in SCFET 2022 IEEE conference, I am going to present this paper ID 96. The title of the paper is Topology and Control Scheme of Machine Side Converter for Wind Power Conversion System. So, the co-authors are Anita Kumari and Dr. C.V. Mahato. So, wind turbine based power generation system comprises of a wind turbine system, electrical generator, a power electronic interface along with some control units as well as protection units. The power electronic interface are widely used in distributed generation system to integrate the distributed resources to grid because of its faster response and higher efficiency as well as reliability. So let's see the basic block diagram of a wind power conversion system, where there is a wind turbine, there is a electrical generator where we are using a PMSG, permanent magnet synchronous generator, a machine side converter and a grid side converter. So the machine side controller and grid side controller are also available. So let's see the passive rectification. In the passive rectification, a simple diode bridge rectifier is and as well as a DC-DC converter is used. So the DC-DC converter works on the MPPT principle. The duty cycle of the DC-DC converter can be changed with the MPPT. Now coming to the circuit diagram, the power circuit of this particular scheme is there is a 6 pulse rectifier with a filter and there is a DC to DC boost converter. So what are the limitations of this particular scheme? The limitation of this particular scheme is lower order harmonics in diode rectifier does not meet the standard IEC 61000 and IEEE 519 standard. In the modeling perspective, the switching model of the line commutated diode bridge rectifier is discontinuous in nature, and developing small signal model of diode bridge rectifier is time consuming as well as challenging in nature. Therefore, average model of the diode bridge rectifier is preferred. So as you can see, is line commutated diode bridge rectifier without any source impedance. The line current is non-sinusoidal in nature, so that we are getting a THD, total harmonic distortion, of around 30%, more than 30%, so which is very higher side. So with a source impedance, there is a slight change in the line current and the line TSD is around 22%, so that's still a higher side, and we are getting a because it's a 6 pulse diode rectifier, we are getting a 5th order harmonics as well as the 7th order harmonics, and NP plus minus 1 the formula. According to the NP plus minus 1, we are the first harmonic is the 5th and the second harmonics is the 7th order harmonics. So then 11th and 13th order harmonics is there, and the fundamental is always there. So what is the this is basic limitation of a line commutated diode bridge rectifier. So what are the limitations of the boost converter? The limitations of the boost converter that practically the conversion ratio of the boost converter is 4 to 5 times. This is due to some parasitic components, the capability of hardware, limitations of the switches as well as hardware, and boost converter exhibits non-minimum phase behavior due to presence of a right half plane 0, and the performance of the boost converter degrades with higher duty cycle. So to reduce the input side harmonic, there are different ways. One of the way is to implement harmonic filters, but those filters are bulky, expensive, it's difficult to tune those filters, passive filters. Another approach is to use a multi-pulse diode rectifier with phase shifter transformer. In this particular paper, we have used a 12 pulse diode rectifier, where though the 5th and 7th harmonics of the 6 pulse rectifier is mitigated, but there still exist 11th and 13th order harmonics. So this is the basic circuit diagram of a 3 pulse 12 3-phase 12 pulse diode rectifier with boost converter. As you can see, the line current and the line current harmonics, we are getting the 11th and 13th order harmonics. What are the basic limitations of the passive rectification? The substantial reactive power drawn by the rectifier increases the volt ampere rating. There is a voltage drop at the bus. The higher input current harmonics results in distorted line current. The increase in harmonic as well as thermal loss of the transformer. Electromagnetic interference with communication line. Overheated neutral due to excessive neutral current due to triplen harmonics. So that's why we use boost type active rectifier. This is a very classic boost type active rectifier where we have 6 switches, and this is the parallel connection of the boost type rectifier connected to the PMSG, which is further connected to the wind turbine. And apart from that, we have diode clamp, which we have the diodes are there, more number of diodes are there. Then the capacitor clamp. In the capacitor clamp, apart from diode, there are capacitors. And the final kind of topology is a VNR rectifier. There are 2 different kind of VNR rectifiers, 2 different variants of VNR rectifier. One is 4M0D and one is 1M4D. So this is the basic circuit diagram of 2M0D variant of VNR rectifier, where you can see there are 4. So there are MOSFETs over there in the bidirectional configuration, and for that unidirectional power flow, and it's a 4 quadrant switches. And so from the two of the variants, 2M0D variant of VNR rectifier is preferred because of packaging issues as well as low rating. And if you compare the VNR rectifiers with diode clamp and capacitor clamp, we can see the number of diodes, reduced number of diodes, reduced number of IGBTs, and reduced number of IGBT gate driver in VNR rectifier. Apart from VNR rectifier, we have Swiss rectifier, and we have mini toaster rectifier where zigzag transformer is used. So coming to the loss part, there are 2 different kind of basic losses, that is conduction loss as well as switching loss, and this are the expression per conduction loss as well as the switching loss. So apart from topology, coming to the generalized block diagram that we have this is the generalized control scheme of the active rectifier, where we have a ABC to DQ transformation. The ABC to DQ transformation is provided to 2 different current controller, that is one is D axis current controller and second one is a Q axis current controller, and then again it has been converted to DQ to ABC, and modulation SPWM modulation is provided. And the speed controller is the power and speed controller is also provided. So there are 3 different control loops. One is a speed controller, second one is a D axis current controller, and third one is a Q axis current controller. In this particular manner, the active rectifier is controlled. So basically this paper provides a very brief idea about different passive as well as active topologies that can be used in machine side converter of a wind power conversion system. So the machine side converter the loss calculation has been discussed, and the generalized control scheme of the converter has also been discussed in this paper. Thank you.